Welcome back. In this video, we're going to take a bigger look or more in-depth look at the electric field inside a set of parallel plates. Okay, we mentioned this the other day that this is a very, very useful setup in order to study electric fields. So what we have here is a negatively charged particle with a charge of negative 1.2 times 10 to the negative 17th coulombs and a mass of 1.254 times 10 to the negative 25th kilograms is placed between oppositely charged parallel plates. Here's the picture. Positive plate, negative plate. At which location between the plates, A, B, or C, is the electric field and therefore the electrostatic force the strongest? Remember, electric field is E equals Fe over Q, where Q is just the test charge. So the test charge right here is our negatively charged particle. Very small charge, does not affect the electric field inside the plates. So if the electric field gets bigger, then if the test charge remains the same, that means Fe must have gotten bigger. But what did we remember? What did we learn about electric fields? We learned about for electric fields inside a set of parallel plates. Between the two plates, the electric field is uniform throughout. So it is actually equal for each location. And again, that doesn't mean that every set of parallel plates has the same exact electric field. It just means that inside this particular set, the field is the same here, here, and here. I could change the field if I wanted to by compressing the plates closer together or by changing the charge that is on either of these plates. Matter of fact, as I mentioned in a previous video, that's how the buttons on this calculator work. When I press down on them, it changes the electric field in a set of parallel plates beneath this, and the computer inside the calculator reads that and says, oh, they must want an 8 displayed on the screen, so it displays an 8. Okay? Draw arrows to indicate the direction of the electric field. We know electric fields always go from positive charges to negative charges, and the closeness indicates how strong the field is. So if the field is the same strength everywhere, the arrows should be evenly spaced apart. So if I want to draw the field, it should look something like this. Evenly spaced field lines. Or at least as evenly spaced as I can make them. Probably noticed by this point, I am not exactly an artist. Oh, that one's too big. Oh well. You guys get the point. Evenly spaced field lines. I didn't have to draw this many, but once I started, I just kind of had to keep going. Okay. A positively charged particle is shot into the plates at a high velocity. Sketch its path in the diagram above. So I'm going to put like a little plus sign here to indicate, hey, a positive particle is coming in. Or maybe you put a P for proton. I don't really care what you do. Now, if it gets shot in, okay, gets shot in like this. Now, what's that going to do? The positive particle is going to be repelled from the positive charges and head towards the negative charges, right? Right. So if we don't shoot it in very fast, it's going to go right there. If we shoot it in faster, it might make it farther. If we shoot it in really fast, it'll go all the way through, but the path will be deflected. Possibly like this, okay? And then it will keep going in this direction afterwards. Okay, so what happens is if we shoot charged particles inside the parallel plate, we can actually alter their path. And I alluded to this the other day. This is actually how, I'm not sure if it's still how television screens work, but it's definitely how some old screens work. This is the idea behind this. You can make something called a cathode ray, which essentially shoots charged particles. You run them through a set of charged plates, and it will actually deflect the particles to different places on a screen. And when they show up on the screen, they'll make like a little mark. And if you have enough of these particles, if you have enough of these particles getting shot out in a very small span of time, and if you can vary the electric field in these plates to shoot them out to different locations, then what you can do is create a picture on a screen. And this is how the very first screens actually worked, okay? You had these electrons, or these charged particles, I don't know if they're electrons, getting shot at a screen, showing up, and then therefore you would get a picture on the screen. So old screen technology, that's how it worked. Okay. If the magnitude of the electric field on the particle is 1.025 times 10 to the negative 7th newtons per coulomb, what is the magnitude of the electrostatic force on the particle? So we know the field, we want to know how big the force is. This should be pretty easy. E equals Fe over Q. The field is being created by the parallel plates. I don't have to know the size of the charge on the parallel plates because Q is the test charge. That's the charge that is, let's say here. Okay, so that's the charge that is getting, hold on one second. Let me just make sure I have the right one here. Sorry, sometimes when I look at my notes from previous years, I have to look a little bit. Okay, all right. So yeah, okay, the charge so we're not talking about this positive one. We're talking about this charge up here. So the charge that was at either A, B, or C, okay? This was just kind of like a little sideshow. So if the magnitude of the electric field on the particle that from the negatively charged particle up here is 1.025 times 10 to the negative 7th newtons per coulomb, what is the magnitude of the electrostatic force on the particle? Again, that particle has this much charge. This is our test charge here. So we have an electric field of 1.025 times 10 to the 7th, negative 7th, excuse me, newtons per coulomb equals, there's Fe, and the charge on this particle is, I'm not going to put the negative in, 1.2 times 10 to the negative 17th coulombs. Now, let's actually test something. How big of a charge is this? How many elementary charges is this? We can do this off to the side. If we do 1.2 times 10 to the negative 17th C, let's convert that into elementary charges. We know one elementary charge is 1.6 times 10 to the negative 19th. 1.2 E17 divided by 1.6 E negative 19. We get 75. So this is 75 elementary charges, and in this case it's electrons. So basically you have a particle that has 75 excess electrons, 75 more electrons than protons on it. Okay, just a little sideshow so that we could see what this particle is actually made out of. Now, given this electric field and the size of our test particle, we find that the electric field is, after all of this diversion, approximately 1.23 times 10 to the negative 24th newtons. That's the size of the electrostatic force on this particle. And which way would this force point? If the particle is somewhere in here, well, it's a negative particle, right? The negative will get repelled from this plate and attracted to this plate. So that's an upward force. What if we want to find the magnitude of the force of gravity, or in other words, the weight of the particle? That's easy enough. We know that weight is just Fg equals mg. Weight equals, let's see, the mass of the particle, 1.254 times 10 to the negative 25th kilograms. G, 9.81 meters per second squared. Okay, and interesting. We get 1.23 times 10 to the negative 24th newtons. The force of gravity will pull down on this object. So, interestingly, if I were to draw like a little free body diagram for the particle that's trapped inside, not the one shooting through, the one that's trapped inside or placed inside these parallel plates. So here's our particle, here's our axis. We have the electrostatic force going up, we have the force of gravity pulling down, and those two are exactly the same, and I can't think of any other forces that would be on this. The forces on the particle are actually balanced. So what does this mean? If the forces are balanced, that means it can't accelerate. It could have a constant speed up or down, or it could just hover. or move with no A. But it's not, this particle won't accelerate up or down, okay? It won't speed up upwards or downwards, or slow down in either direction. It will just hover or move at a constant velocity, which would be very interesting if we could see this or detect it. And as a matter of fact, someone had this idea a long time ago. This is not something I thought up of. This is the basis for what is known as the Millikan oil drop experiment, one of the most famous experiments in all of physics. The Millikan oil drop experiment. And I actually asked you to possibly look, I think I asked you to look this up on another homework to give you an idea. This is very, very famous. What Millikan did is he took charged oil drops and suspended them in an electric field. So he did this exact same thing, and he got them to where they were just kind of hovering in this electric field. They had an electrostatic force up on them and a force of gravity down. What he did was, based on the size of the oil drop, he determined their masses. Okay, and once he had the mass, he could find the force of gravity on that oil drop. And once he had the force of gravity, he knew that was equal to the electrostatic force. Okay, and once he knew the electrostatic force, he could determine, because he knew what the electric field strength was. He used that to find the charge for each drop. And he noticed, okay, so let me run through that again because that's a little confusing. He looked at each oil drop, and based on the size of the oil drop and knowing the density, the density of oil, he could figure out what the mass of each oil drop was. If he knew the mass, he could find the force of gravity. And if he knew the force of gravity, because in this case, since the particle was not accelerating, that must be equal to the electrostatic force. And since he knew the electric field strength, because he had these parallel plates set so that he could figure out the electric field strength. Since he also knew that, he could plug in the electric field strength, the electrostatic force, and solve for Q, the charge trapped in between. And he found something very, very interesting. Okay? He found that the charges were always multiples of a certain number. Okay? He found that the charges, they never had any variation to this. The charges were always multiples of some certain lowest common denominator, I think you would call it. So, this led him to make the realization that we have actually talked about in class. Each drop must therefore have a whole number of electrons. This led him to realize that there is such a thing as what's called quantized charge. Charge only comes in certain amounts. That's why he was essentially seeing multiples of this certain amount. So whether it was, in this case, 75 times the amount or 20 times the amount, he always saw multiples of this certain lowest possible or smallest possible amount of charge. So what he was able to do is figure out what that smallest possible charge is, and that is how he figured out the charge of a single electron. A very ingenious way to do this. Okay, he suspended the particles in an electric field where they had an equal upward and downward force on them. Because he could find the mass, he was able to calculate the downward force of gravity. Therefore, he also knows the upward force. Since he also knows the electric field strength, he's able to find the charge. And when he looked at the pattern of all the charges, he saw that it was always a multiple of some smallest number, implying that that smallest number must be the charge of a single electron. One of the most famous results in all of physics, and that is how we know this number right here. One elementary charge is 1.6 times 10 to the negative 19th C. This is just a good experiment. I suggest you familiarize yourselves with this experiment because it is very, very important. That's it for electric fields. Like I said, this is a tricky subject. If you have questions, please feel free to contact me. I am more than happy to answer any questions you may have. Make sure you understand that what an electric field is, the kind of definition I gave you, alteration of space around a charge. Make sure you can draw electric field lines. Make sure you can calculate with electric fields, and make sure you understand this Millikan oil drop experiment. It's very, very important. So I'm going to leave you there. We are basically at this point 1/2 of the way through electricity. We have done the electrostatics part of this unit. We'll now, there might be one other thing in electrostatics, but it's really, that kind of plays more into circuits. We will now go into the circuits part after this. So I just want to take this time to make sure that you know, please ask me any questions you may have. I'm more than happy to help, and I will see you guys soon. See you later.